Hey fellas, welcome to A12, the area between curves. You're almost done. So, we want to find the area between F and G here. Their intersections are at A and B. So if I do the integral from A to B of f of x, I will get this whole region. And then if I subtract away the integral from A to B of G, this area, or excuse me, this definite integral will give this blue piece, right? So first, we get the whole thing, then we take away this little piece, and we're left with the area beneath the curve. And we are always going to take the integral of the one on top and subtract the one at the bottom. This one looks a little different because G is not non-negative on the interval. And the last lesson, you did some integrals, evaluated some definite integrals where the interval was below the x-axis, and you found that it just gives you the opposite of the area. So notice then that if we do the integral of f of x from A to B, we will get this guy here. And if we subtract the integral from A to B of G, remember that this definite integral is a negative number. So if we subtract it, it will end up being added, and we will have the whole thing. Okay? Can you see my next one? Let's move over a little bit. Okay, here, same thing. We want this area here, but since f is above g, we're going to do the integral of f minus the integral of g. So the integral of a to b of f of x dx is going to give us this number. It's going to give us that area, but remember it's going to be negative. Okay? Then we are going to take and subtract the integral from a to b of g. And remember, this definite integral is going to give us this whole thing. But it is also going to be negative. So we have a minus, which gives us a positive, and this blue definite integral is still this area under the curve, which is going to be negative as well. So we're minusing a negative, which is this whole area, which makes that positive. And once again, since our area in blue here is going to be negative, it will be subtracted out, and what will we be left with? Just that area in the middle. Very nice. My words were kind of funny, but I think you got the gist of it. Okay, a nice example here. Ooh, look at that. The sine and the cosine intersect infinitely many times and make infinite regions like this, all of the same area. Let's find the area of one of them, shall we? I knew you would want to. So, certainly the sine is on top, so we're going to have to do the integral of AB of sine minus the integral from A to B of the cosine of x, but where do these things intersect? That's a good question, huh? Where is the sine of x equal to the cosine of x? And maybe you can just think about it. Right? Where on the unit circle would that happen? Are you getting it? If not, you can divide both sides by the cosine. And remember, the sine over the cosine is the tangent. So where is the tangent equal to 1? Where on the unit circle are the x and y coordinates the same? Right at pi over 4, huh? That's a nice unit circle. And also where? Right here, at 5 pi over 4. Aren't those unit circles nice? Goodness, they're great things. Okay, so let's get after this guy, huh? So we're going to do, that means that this is pi over 4, by the way. And right here is 5 pi over 4. So let's check it out. The integral, the sign is on top. The integral of the sine of x from pi over 4 to 5 pi over 4 is the integral of the sine is the opposite of the oops. Let's do the whole thing at once, shall we? Minus the integral of the cosine from pi over 4 to 5 pi over 4. And I think I'm going to run out of some room here. So we will erase this and move over this way a little bit. Okay, the integral of the sine of x is the opposite of the cosine. So I'm going to come over here and I'm just going to say the area is equal to the integral. I'm going to take, can you see everything I'm doing here or no? Now you can. The area is equal to the integral of the antiderivative of sine is the opposite of the cosine of x, and we have to evaluate that at both 5 pi over 4 and pi over 4. And then we are going to subtract the integral of the cosine, which is the sine, antiderivative, excuse me. And we are going to evaluate that at 5 pi over 4 and pi over 4. And so, the opposite of the cosine of 5 pi over 4 minus the opposite of the cosine, these square brackets, minus the opposite of the cosine of pi over 4. Okay? Minus the sine of 5 pi over 4 minus the sine of pi over 4. So let's do each one of the little parentheses first. This is 5 pi over 4. At 5 pi over 4, we're at minus square roots of 2 over 2, but we want the opposite of that. So we have square root of 2 over 2, positive square root of 2 over 2. This is a minus, so it's a plus, the cosine of pi over 4, which is square root of 2 over 2. Again, here we are. The sine of 5 pi over 4 minus square roots of 2 over 2. And minus the sine of pi over 4, which is square root of 2 over 2. Oh goodness, look what we have here. Square root of 2 over 2 plus the square root of 2. Square root of 2. Minus square root of 2 minus square root of 2 over minus square root of 2 over 2 minus square root of 2 over 2 is negative square root of 2, but it's minus and minus, so plus square roots of 2 or 2 square roots of 2. There you go. That is the area between the sine and the cosine curve. 2 square roots of 2. What a number, huh? Hey, let's do another one, shall we? Just one more. Whoa, look at this animal. We want to find the area between those two curves. And notice that over here, this is f of x equal to 3x cubed minus x squared minus 10x. Here is g. Here, f is greater than g. All right, so we're going to have to do f minus g on this interval. On this one, g is greater, so on this interval, we are going to have to do g minus f. Okay, so we're going to have two definite integrals, and we have to find those points of intersection. So let's do 3x cubed minus x squared minus 10x is equal to minus x squared plus 2x. This is going to be simpler than you think. 3x cubed. Add an x squared, it disappears. That's nice, isn't it? And then subtract 2x, and we get minus 12x equals 0. Oh, that makes things really nice, doesn't it? Because we can do 3x times x squared minus 4 equal to 0. Difference of squares, so 3x times x plus 2 times x minus 2 equal to 0. So what are the zeros? X equal to minus 2, 0, and 2. Very nice. So here we got minus 2. Zero, which we already knew, I guess, and positive 2. So, whoo-wee. Let's see how much of my board you can see. Okay. The integral from minus 2 to 0 of 3x cubed minus x squared minus 10x, and remember that a difference of an integral, a difference of integrals is an integral of differences. So I'm going to write this like this: minus x squared plus 2x dx. That's the first integral. The second integral, we will so that's right here. That integral will give us this area. The next integral that we have to add to it is plus the integral from 0 to 2 of minus x squared plus 2x minus 3x cubed minus x squared minus 10x dx. I should really put these in square brackets so that nobody gets confused when they come and look at my work. So, see, we have just flopped them. We have the integral of f minus g first, and then the integral of g minus f next. I put them all together, and this is kind of a lot of work, but not too much. What does that mean, huh? Minus 2 to 0. 3x cubed minus x squared plus x squared, those disappear, minus 10x minus 2x. That, huh? Okay, that's one of them. And over here we have the integral from 0 to 2, minus x squared minus 3 is minus 4x squared, or x, minus 3x cubed, or x squareds disappear, minus x squared plus an x squared, and then a plus 2x minus plus. Okay? Ooh, look, those are opposites of each other. Watch this, I'm going to do something. The integral from minus 2 to 0 of 3x cubed minus 12x. I'm going to make this a minus. And then I have the same integral here. Well, the same function in the integral, different bounds of integration. But that makes things a little easier for me, right? It's much easier for me to think of. So, what is the integral of 3x cubed? We have 3/4 x to the 4th minus 6x squared. We are going to evaluate that at 0 and 2. And then we have the subtraction. Well, it's the same thing. 3/4 x to the 4th minus 6x squared. Our bounds of integration are 0 to 2. Oh, this is supposed to be minus 2 here. Okay, we're getting there, huh? It's a little bit monotonous. The computers can do this really quick for you guys. So, I'm going to keep them in square brackets, and I'm going to say 3/4 0 raised to the 4th minus 6 times 0 squared. That's the first time when I put 0 in there. Then I have to subtract, and I have 3/4 minus 2 raised to the 4th minus 6 times minus 2 squared. That's the first. And then we have minus 3/4 2 raised to the 4th minus 6 times 2 squared. That's the first one. Minus, ooh, this is going to be easy, huh? This one. 3/4 times 0 raised to the 4th minus 6 times 0 squared. Okay. Whew. Zero minus 2 to the 4th is 16. 3/4 of 16 is 12. This is 4/24. So this is minus 12. Uh-oh. Let's just keep going. 0, this is, what did I say this was? Minus 12. 0 minus minus 12 is a positive 12. Oh, this will work out nicely. This one goes to 0, and this we just said is 12, or minus 12, so we have 12 minus a minus 12, and then 24. So pardon my getting freaked out for a little bit there. I thought things were going to go haywire on us. But the area of the region between these two curves is 24. Okay? So those are a little kind of monotonous. Make sure that you can do this on some of the ones that are a little easier, and then perhaps use GeoGebra to do some integrals too. Okay, I want you to make sure that you can go through this process, but I don't want you to kill yourself because it's going to take forever to do it for everyone. So, make sure you can do it. Use GeoGebra when you get the hang of it. I love you guys. Woo, 7